The pressure structure in an atmosphere is simple. The pressure drops as you go higher up. But the temperature structure is a lot more complex. Any atmosphere has to have heat applied to it to keep the gases from freezing. So all atmospheres have one or more heat sources. However, the different heat sources can cause the temperature to go up or down depending on altitude, latitude, season, and time of day. We're going to start out by just considering how temperature changes with altitude. Later, we'll look at some of these other factors. To give us a starting point at understanding temperature structure, we should begin with a baseline temperature for a planet. This is called the no greenhouse temperature, or NGT. The no greenhouse temperature is a simple, predicted global average surface temperature for a world. Let's break that phrase down to see what it means. When we say simple, predicted, we mean that it's based on a single, simple assumption that direct absorption of sunlight is the dominant heat source. The actual temperature on the surface of a world may be quite different from this if this assumption doesn't actually hold. As we'll see later on, a planet with substantial greenhouse warming can have a much higher temperature than this. The next part of the statement is that this is a global average. We know from experience here on Earth that the surface of a planet doesn't have just one temperature. Instead, different parts of the surface can have very different temperatures. However, by starting with a global average, we can begin to understand the conditions on a world. Lastly, this is just the surface temperature. The temperature of a planet's atmosphere can be much higher or lower than the surface temperature depending on the elevation, which we'll look at shortly. We should look more closely at the basic assumption behind the no greenhouse temperature. The idea that the surface temperature depends mainly on sunlight. Obviously, this means that a planet closer to the sun should have a hotter surface than one that's farther away. Note that this is different from the internal heating of a planet, which depends much more on other sources of energy, and so has little to do with the sun. It's important whenever you're talking about how hot a planet is that you be clear on whether you mean the interior or the surface, since they can be very different. For example, Jupiter's cloud top temperature is cold enough to freeze ammonia, while its interior gets as hot as the surface of the sun. On the other hand, Mercury's surface is hot, but its interior is not warm enough to power any geologic activity. So when we think about heating the surface of a world by sunlight, we return to something we saw several chapters ago: the 4 ways light and matter can interact. Remember that matter can absorb, emit, reflect, and transmit light. Planets aren't transparent, so they don't transmit light. Instead, the sunlight a planet receives is either absorbed or reflected away. The fraction of all of the light reflected away is called the reflectivity, or the albedo. A reflectivity of 1 means a perfect reflector, something that reflects all of the light that hits it. While no object is a perfect reflector, some common materials like clean snow or ice can reflect well over 90% of the light hitting them. A reflectivity of 0 means a perfect absorber, something that absorbs all of the light that hits it and reflects none. There are no perfect absorbers either, but very dark materials like soot can absorb over 90% of the light hitting them. A planet is only heated by the light it absorbs, and the higher its reflectivity, the less energy it will absorb. In other words, darker planets get hotter than lighter planets. Of course, as a planet's surface heats up, it will emit light out into space. The amount of light it emits depends on its temperature. When the amount of energy the world emits equals the amount of energy it's absorbing, then it will reach an equilibrium and stay at that temperature. This is the no greenhouse temperature. This figure summarizes the no greenhouse temperature. The sunlight coming in is mostly visible light, shown in yellow. Some of this is reflected away, so it doesn't play a role in heating the planet. The rest is absorbed by the planet, which then emits the light as infrared light, shown in red on the diagram. When the amount of infrared emitted equals the amount of visible light absorbed, the planet has reached the no greenhouse temperature. Here's a chance to test your understanding of the no greenhouse temperature. Saturn's moon Iapetus has a very unusual surface. Part of the surface is covered by dark, tarry material, while the rest is covered with light, icy material. Since both sides get the same amount of sunlight, which side should be hotter, and why? We know that the no greenhouse temperature is a prediction of the average surface temperature on a planet. So now we need to look at how this prediction actually holds up against reality. Here's a table listing all 4 terrestrial planets and the Earth's moon. It shows the distance, albedo or reflectivity, and spin rate. It also gives the no greenhouse temperature and the actual surface temperatures on these worlds. For some of them, the match is pretty good. Mars has a no greenhouse temperature of 218 Kelvin and an actual temperature of 223 Kelvin, just 5 Kelvin difference. Mercury and the Moon have huge changes between their day and nighttime temperatures because they both spin very slowly. However, the average is still close to the no greenhouse temperatures, 440 Kelvin for Mercury and 273 Kelvin for the Moon. For the Earth and Venus, the no greenhouse temperature isn't such a good description of what's going on. On Earth, the actual temperature is 288 Kelvin, almost 40 Kelvin warmer than the no greenhouse temperature. This is a good thing for us. Remember that water freezes at 273 Kelvin. So if the Earth were at its no greenhouse temperature, most of our oceans would probably be frozen. Something is keeping the Earth warmer than our simple model predicts. Venus is much worse. First, notice that the no greenhouse temperature for Venus is actually lower than Earth, only 230 Kelvin, even though Venus is closer to the Sun. The reason for this is reflectivity. Venus reflects 70% of the Sun's light away, as opposed to only 36% for Earth. Venus is covered with thick white clouds that reflect sunlight very efficiently, so reflectivity can even overwhelm a difference in distance from the Sun in the no greenhouse calculation. But the actual temperature of Venus is ridiculously hot, 740 Kelvin, even hotter than the daytime side of Mercury. Clearly, this is a case where the no greenhouse model has completely failed. Something else is going on here. The process you've just worked out in the last couple of questions is called the greenhouse effect, and it makes a world surface hotter than you would expect from the no greenhouse temperature. The greenhouse effect is caused by gases like carbon dioxide, water vapor, and methane. These gases are all transparent to visible light, so sunlight passes through them easily. But they absorb infrared light, especially the long wavelength infrared light planets emit because of their surface temperature. So visible light from the Sun passes through the atmosphere and warms up the ground. But when the ground re-emits this energy as infrared, the light can't escape very easily because it's being absorbed by the atmosphere. This causes the lower atmosphere to heat up, also warming up the planet's surface. In effect, greenhouse gases trap heat energy near the surface. This picture illustrates what's going on. The yellow visible light comes in and is absorbed by the ground, while the infrared, shown in red, is absorbed and re-emitted by the atmosphere many times. Eventually, that infrared light will escape through the atmosphere, but in the meantime, the air and ground can get hotter. Here's Bruce reminding us to be careful here. The greenhouse effect doesn't depend on a planet's reflectivity or distance from the Sun. It also isn't mostly about the atmosphere absorbing sunlight. Instead, it's all about the presence of greenhouse gases in the atmosphere, trapping energy from the ground. So, if you're trying to decide if greenhouse warming is likely for a world, the first question to ask is, does this planet have an atmosphere? On the other hand, if you have evidence that there is greenhouse warming on a planet, then you can be sure that there must be an atmosphere present. Let's look more closely at greenhouse warming on Venus and the Earth. Venus is the poster child for greenhouse warming. Its atmosphere is much thicker than Earth's, and it's almost entirely made of carbon dioxide, a strong greenhouse gas. This has the effect of making Venus 500 Kelvin hotter than its no greenhouse temperature. So we say that the amount of greenhouse warming on Venus is 500 kelvins. The conditions on the surface of Venus are appalling. The high pressure and temperature makes it even difficult for robots to survive on the surface. This image is one of the few that has been taken from the surface of the planet. It was taken by a Soviet Venera spacecraft in 1981. We can see a piece of the spacecraft in the foreground and a barren, rocky landscape around it, with a little bit of sky in the upper two corners of the picture. Given the harsh conditions, even making a single image like this was a major technical challenge. They had to use polished quartz crystals in the optics. Ordinary glass would have simply melted on Venus. Even with that, the spacecraft only lasted 2 hours on the surface before the electronics shut down. The Earth averages about 40 Kelvin warmer than its no greenhouse temperature. This is a moderate amount of warming, though it is enough to keep most of the Earth above the freezing point of water. Most of our atmosphere is made of nitrogen and oxygen. Neither of these are greenhouse gases, so they don't play a role here. Instead, it's just minor parts of our atmosphere, like carbon dioxide, that drive greenhouse warming. This chart shows the amount of carbon dioxide in the atmosphere over time and compares it to the average global temperature. As you can see, they're closely connected. The more greenhouse gas we have in the atmosphere, the hotter the planet gets. We'll return to this plot later in the course when we talk about climate change on the terrestrial planets, and especially recent changes to the Earth's climate. Remember this table? You should be using it to help you keep track of the equations we use in this course. Fill in the greenhouse effects section of this table now. Keep it and update every time we use a new equation. You'll find this page useful doing homework and reviewing for exams. Depending on your section, you may be required to submit a copy of the completed version for credit.